Okay, welcome everybody. Quasi Geodesics on the Stiefel Manifold. This is from a paper I prepared from the STU Odense in Denmark. So what do I want to talk about? First, I want to introduce tilde. So these times.
Parce que ça va être intense. Ça se trouve, ils s'entendent sur le Zoom.
Efficient Quasi Geodesics on the Stiefel Manifold. This is from a paper I prepared together with my supervisor, Ralf Zimmermann, from the STU Odense in Denmark. So what do I want to talk about? First, I want to introduce the general idea. What are quasi-geodesics and how can we use them in the geodesic endpoint problem? Then secondly, for a known kind of quasi-geodesics, we want to introduce an economy size variation or economy size formulation. Thirdly, we introduce a new kind of quasi-geodesics, which are also economy size, but which are closer to the true geodesics on the Stiefel manifold. And in the end, I show a numerical comparison between the two kinds of quasi-geodesics. So what are we talking about? The geodesic endpoint problem. Well, if we have 2 points on a Riemannian manifold, then the geodesic endpoint problem is to find the shortest connecting geodesic between the 2 points. But this is computationally involved on many manifolds, for example, on the Stiefel manifold. So an idea is to use some different curves, some surrogate curves that share at least some properties with the geodesics, but which are cheaper to calculate. And why is this interesting? Well, this is important for interpolation, for finding Riemannian barycenters, for optimization problems, and for a whole range of other problems. So what are quasi-geodesics? Well, a geodesic on a Riemannian manifold is a curve gamma with vanishing covariant acceleration. And quasi-geodesic, for our purposes, is then just defined as a curve with constant speed and covariant acceleration with constant norm. So not necessarily vanishing, but at least constant. So if you think of R2 with the Euclidean metric, then the geodesics are the straight lines, and any part or any segment of a circle is a quasi-geodesic. From this, you can already see that a quasi-geodesic can, of course, deviate quite a lot from a geodesic, but also that it can be quite close, and especially geodesics are a special kind of quasi-geodesics. We are interested in the Stiefel manifold, so this is, of course, well known. The Stiefel manifold is the manifold of orthonormal frames. So n times p matrices U with U transpose U is the identity matrix, and then the tangent spaces are of this form with U times the skew-symmetric matrix, and then the orthogonal complement times any n minus p times p matrix. And the canonical metric on the Stiefel manifold is just given as the trace of the one tangent vector transpose times identity minus 1/2 the projector on this space spanned by U times the other tangent vector. For this canonical metric, the Stiefel exponential is also well known. So if we have U and a tangent vector, then we can calculate the Stiefel exponential. So we can calculate the geodesic in this form, matrix U orthogonal times this exponential of an n by n matrix times the projection on the first p columns, which is equivalent to taking this matrix U and Q, where Q and R are given by a QR decomposition, and then we have the exponential of a 2p times 2p matrix, and then the projection on the first p columns. This is well known, as I said, but we cannot directly invert this problem for 2 given points. So we can only invert this problem iteratively. And this is exactly the reason why we want to find an alternative, namely the quasi-geodesics. For this, we can make use of the quotient structure of the Stiefel manifold, which is an idea which was already used before for the quasi-geodesics that we'll see later. So the Stiefel manifold, if we have 2 points on the Stiefel manifold, U and U tilde, ideal would be to find the Stiefel geodesic between the 2 points of this form. But as I said, we cannot find A hat and B hat directly. But as an alternative, we can project the entire equivalence class of Stiefel points to the Grassmann manifold, so the manifold of subspaces of Rn, p-dimensional subspaces. And then we can find the Grassmann geodesic going from the one point to the other, which, if we lift the Stiefel manifold, is the Grassmann geodesic from U to a different representative of this equivalence class, U tilde times R, where R is an orthogonal matrix. And then we can take this Grassmann geodesic as a starting point. And this matrix R, which we can explicitly calculate, we can in this equation here, multiply it to the other side, take the logarithm of the R transposed, and denote this by A, and then we know that the matrix U tilde is of this form, which we take as a starting point for our quasi-geodesics. So if we put everything together, then this is exactly how quasi-geodesics have been introduced before by Krakowski et al., namely by taking the Grassmann geodesic and then taking the geodesic in the equivalence class by taking the exponential of t times a. The orange part is the Grassmann geodesic, and together they form the quasi-geodesic between U and U tilde. So this basically is known. It was formulated in a different formulation where we don't have this nice off-diagonal structure of the matrix exponential because it was on the other side of the representative here. And therefore, it was working with n times n matrices. Our contribution now is to reduce this complexity and work with p times p matrices basically in here and reduce the problem to n times p matrices. So as a proposition, we show this kind of retraction if we have given a point u and the tangent vector delta of this form with this singular value decomposition, then the mapping defined like this. So the Grassmann geodesic times this exponential t times a is a curve with the following properties, starting at u with these tangent vectors, which shows that they have constant speed. And if we calculate further, they also have constant norm covariant acceleration, which means that they are quasi-geodesics. And furthermore, from this here, you see that gamma is a geodesic if and only if the product of B with A is 0. How do we find this now for two given points? Well, basically, we make use of the Grassmann logarithm, so the logarithm on the Grassmann manifold, for which we have recently introduced a method to compute it in for n times p matrices, and also finding this rotation matrix R explicitly, or the orthogonal matrix R explicitly, by basically first doing a Procruster step to find the correct representative U tilde times R, and explicitly finding this R, and then, as we have seen before, calculating the matrix A from this, and then just go on basically as usual and finding the Grassmann geodesic times the exponential TA will give us the quasi-geodesic in the Stiefel manifold. And all of this is working with, well, these are diagonal p times p matrices, and all of this is working in complexity n times p. But we also want to introduce a different kind of quasi-geodesics, an alternative kind. For this, we observe that if we take any geodesic in the orthogonal group, of which the Stiefel manifold is a quotient, then this will project to a quasi-geodesic in the Stiefel manifold. So here we look at a special case. If we have U, our starting point in the Stiefel manifold, and then Q, which is part of the orthogonal complement of U, so also an n times p matrix here. And then we have the exponential of a matrix of this form, where A and C is skew-symmetric and B is just any p times p matrix. Then we will see that any curve of this form has these properties. So starting at U, here we can calculate the derivative, the tangent vector, and we can see that these curves have constant speed and constant norm covariant acceleration of the form Frobenius norm C times B. And here you already see if the matrix C would be 0, well, kind of obviously, then we would have the true Stiefel geodesic. So our aim is to find matrices A, B, and C with C as small as possible, such that we can calculate quasi-geodesics between two given points. We go about this problem in the following way. First, we use our observation. We can reduce the size a little bit by making use of the singular value decomposition, but basically we use our observation that we already have seen that U tilde is of this form, U times Q, and then the exponential of this off-diagonal matrix, this projection on the first B columns, and then times the exponential of A. But if we move the exponential of A to the other side of this projection matrix, then we see that this equation is equivalent to this equation, where we just have any skew-symmetric C in the bottom right corner here, because this will just be removed by the projection. But with this, we can now work, because if we see that we have the exponential of this times the exponential of this, then the product will be the exponential of another matrix, A minus B transpose B, C, where this matrix is just given as the matrix logarithm of the product. And if we have the option to change our C, because A and B are given for 2 points, we can choose our C in such a way that our capital C over here gets as small as possible. This is what we want to solve. For this, we want to see how does the capital C depend on our 2 matrices. Well, if we denote them by X and by Y, then we can make use of the Dynkin-Baker-Campbell-Hausdorff formula for this logarithm of the exponential product. And we have 3 facts that are quite useful now because of the symmetric structure of the Grassmann manifold. First, well, the first factor is general, that the Dynkin formulation depends only on iterated commutators of X and Y. But then because the Grassmann manifold is symmetric, the Lie algebra SON for any value of n has a Cartan decomposition in a vertical and horizontal part, where the commutator of 2 vertical matrices is vertical and horizontal is horizontal, and 2 horizontal matrices, the commutator is vertical. And if we have our X and our Y as defined here, then our X is horizontal and our Y is vertical, which means they always, the commutators always keep the diagonal or the off-diagonal structure. And since we are interested in finding the C, so this part of the diagonal structure, which we want to make as small as possible, we can calculate some parts of the Baker-Campbell-Hausdorff formula without exploding in complexity. So if we look at terms up to combined order 4 in X and Y, and just denote the anti-commutator with these curly brackets, then we see that our capital C of C is of the following form. So C plus these terms plus some higher order terms. And if we ignore the higher order terms, then making our C small means we can take a look at the fixed point problem. Capital C of C is equal to 0, which is equivalent to saying lowercase c is of this form, also depending on C on the other side here. So we just take a first step, first single iteration in the fixed point problem, starting from C0 is equal to 0, and then C1 is just minus 1/6 BAB transpose. And if we insert this, we can analyze the problem and see that if we define delta as the maximum of the 2 norm of A and B, if it's smaller than the logarithm of square root of 2, then our norm of C is bounded by this factor, which shows that we can estimate the size of C. And of course, delta depends on our representatives U and B, because A and B are basically, B is given by the subspace distance in a way. So it's because of the Grassmann geodesic between the 2 points, and A is the deviation in the equivalence class. So these, of course, depend on our 2 points, but with this we can estimate the size of our factor C. Okay, if we choose to calculate our small c depending on A and B like this, then we can define an algorithm in a way similar to the first algorithm to calculate short quasi-geodesics between 2 given points. So we go about it in a similar fashion, but then we introduce our factor small c as we have just seen, minus 1/6 BAB transpose, and then we can calculate the product of the 2 exponential matrix, or the product of the 2 matrix exponentials in a reduced fashion by also making use of the structure in the cosine and sine formulation to find our A minus B transpose B and C. And then we end up with our quasi-geodesic between U and U tilde of this form, where our C is bounded, as we have seen before, and our C should be small, therefore. There's a word of caution I want to say, which is that, of course, we can find this quasi-geodesic between 2 given points, but if we have a point and a tangent vector, we cannot directly find the quasi-geodesic of this form in this direction, because we don't know which would be the correct C between these 2 points. But since our aim was to approximate the Riemannian geodesics, we can use the Riemannian exponential as an approximation, and then, for example, calculate the Riemannian exponential in this direction, and then afterwards calculate the quasi-geodesic between these 2 points, depending on the problem we want to solve. For a numerical comparison, we first looked at two random points at different distances on the Stiefel manifold of n equal 200 and p equal 30. So the distances between 0.1 times pi or 0.5 times pi or 1.3 times pi. And here you can see that the Stiefel geodesics with algorithm 2, so the new kind, are considerably closer to the true geodesic than the quasi geodesics of algorithm 1. Since they are closer, they are also shorter. And we see this in the second comparison, where we have calculated for different values of p the length deviation between the quasi geodesic and the true geodesic between two different points at a distance of pi over 2. And here you see for a dependence on p, the first kind of quasi geodesics have a length deviation always about 10 to the power of minus 3, while the second kind of quasi geodesics are considerably closer, as you can see here. But the exact p dependence of this length deviation is still an open problem. So with this, we come to the conclusion and the outlook. So as a conclusion, if we have 2 points on the Stiefel manifold, we have first proposed a new efficient representation for a known type of quasi-geodesics. So now they are suitable for large-scale computations. And the exact inverse of these quasi-geodesics is given by a retraction. And we have introduced a new type of quasi-geodesics which are closer to the true geodesics, and they are also suitable for large-scale computations. But for those, the exact inverse is not known. So as an outlook, we'd like to study the length properties of these new quasi-geodesics especially, and the p dependence of the length deviation. So here are some references that we have used. And with that, I'm left to say thank you very much for your attention. And are there any questions?